Well, thank you very much, Tavy. Thanks very much indeed. I'm delighted to be here, delighted to be invited to talk in this series. I know I'm a colleague of Tavy's, but still it is a real great honour, especially having seen all the talkers that have gone before me over the last few months. It's really nice to do that. I don't know about inspiring, but I will do my best. And I thought I would start by just mentioning that I've had pretty good lockdown. I've had a pretty good year of pandemic. Nothing really bad has happened to me or my family, so I've been very, very lucky indeed. I guess the one big outcome really is that we now have an outdoor wood-fired pizza oven to use. Sadly, I didn't get it finished in time for last summer, but looking forward to that this summer. And as Tavy said, I'm going to talk a little tiny bit about my career, not bore you, because actually I wasn't always a glaciologist. In fact, my PhD was all about face recognition and neural networks, and this was my very first paper over a quarter of a century ago, a few years after my PhD, in neurocomputing. Who knew such a journal existed? When I eventually got into remote sensing, it wasn't to do glaciology. No, indeed, it was to look at tropical forest biomass density, and this is where I got into using synthetic aperture radar. I also had a little dalliance here with looking at urban areas, and that was quite a lot of fun too. But it wasn't until I moved to Swansea, teamed up with Tavy, and was working on this kind of thing for a couple of years before, I think 19 years ago, when I published my first paper in glaciology with Tavy on the surge of Monica brain in Valbard. Along with Tazio as well. I learned an awful lot of things from Tazio, as we'll see shortly, not just interferometry, but also feature tracking and speckled tracking. And in fact, this paper was published so long ago that Monica brain has surged a second time since that paper was published. So anyway, that's the history. I want to move on now to when my obsession was born, my obsession with remote sensing and glaciers, and that was really this paper here. Tazio had taught me feature tracking, and I went data mining through the ERS1 catalogue and produced a time series of velocities and isofront positions from these very famous glaciers now, Helheim and Kangerlussuaq, and managed to produce this rather wonderful result here, showing how the frontal position went backwards, the velocities went up, and we got this lovely seasonal pattern. And this was the start, I think, of a lot of activity in Greenland. So that was my obsession born then. I saw how easy it was to get some really interesting results looking at feature tracking of glaciers. And what does this bring me on to doing now? Well, as I'm sure most of you know, the EU Copernicus program launched a series of satellites called Sentinel-1, which has on board a synthetic aperture radar, better than the ERS, better than many of the ones that came before it. And in fact, in 2014, Sentinel-1A was launched, giving us a 12-day repeat feature tracking, which was an order of magnitude better than ERS or Envisat that come before it. And then they went even one step better and launched Sentinel-1B, an identical satellite in 2016, to giving us 6-day repeats. Now, this was really amazing improvements in the quality of feature tracking from glaciers, particularly in Greenland. So as a result of this, since 2014, basically, I've been in hog heaven just playing feature tracking with Sentinel data. I've been fully occupied with this, and my habit has now reached about 1 terabyte a month. And really, this is sort of, where I got stuck, really. This is what I'm doing now because I got hooked on it, and that's where I spend most of my time. So I'm on a cycle now. Sentinels have a cycle of 6 days, so I'm a slave to that cycle, downloading the data, trying to do something with it. It has many advantages. It had some disadvantages as well, because I never seem to finish anything anymore, because I'm always trying to catch up with the latest data that comes down. But there are some advantages as well. For instance, I can make new discoveries because the Sentinel data comes at near real time, so I can have a velocity map maybe at the same day that it's acquired, maybe the day after. Also, with so much data at such a repeat 6 days, such reliable data from radar satellites gives me the ability to create engaging animations, which is great for teaching, great for engagement, great for outreach and that kind of thing. And having all these nice things to do gives me a great chance to work with a lot of very interesting people. Now, rather than try and do wall-to-wall velocity maps like people like Eric Mignot, Ian Jockin and others have done and do really, really well, that's the bedrock of remote sensing in glaciology, I've chosen a different path, and I choose some particular areas and I look at those in more detail. I look at those sort of every cycle to see what the temporal changes in velocity are. And these are my areas of interest. And I'm going to say a little bit about these ones down here in red. What I'm going to try and do today is to share with you some of the results that I've got sitting on my hard disk, some of which have never seen the light of day. I'm not really going to try and get to any conclusions about this. I'm just going to really share observations with you. And as a result, I'm not going to look at the literature. I'm not going to do you the service of seeing what papers you've written about these things. So forgive me for not citing any of your papers or looking back at recent history of what's been done on these glaciers, and just allow me to indulge you by showing you what I've seen in what's happening in these glaciers from the last few years of data from the Sentinel satellites. So before I do that, I ought to say something for those of you who are not familiar with feature tracking. Now, feature tracking is quite a simple method. Basically, you measure displacements by cross-correlation of image patches between a pair of images separated by, in this case for Sentinel-1, 6 days, which is a nice kind of repeat. And if you take a couple of images, as you can see here, if I step between them, you can see the fact that that glacier is moving. And by automatically tracking those features, then you can get a velocity map like the one on the right here. And the speckle comes in because this is radar data. And even when there aren't visible patches, visible patterns here to track, you can often get good results because the speckle correlates and you get really good results, particularly in Antarctica. So it's a simple method, but it does have some complications because the synthetic imaging radar, of course, has an interesting imaging geometry which we have to deal with. The fact that it's looking sideways into the scene, and any upwards and downwards motion of ice with the tide is seen as a displacement in and out of the look direction, so that has to be corrected for. Data volume is another interesting issue to deal with, and this is not traditionally what you might think of as data volume, you know, the 1 terabyte a month that I'm trying to process. Actually, that's quite easy to deal with because even on a reasonable workstation, which is what I work with, it's quite possible to download that data automatically and process it pretty readily. Really, the problem with data volume for Sentinel-1 is actually being able to look at the results and spot the interesting things that happened over the last week. So I make a great effort in trying to visualize the results as they come down, rather than just accrue data, process it all at once. I do try to visualize it, look at it, and share it with other people so we can get a good idea about what's going on. And finally, to summarize this data, you've also got to have a very good filter, because as those of you who do feature tracking know, it doesn't always work very well, and you've got to be able to sort out the wheat from the chaff. So if you've got a good filtering algorithm, then you're onto a good thing. So that's the method out of the way. Let's move on now to the results. So this is just, as I say, sharing with you things that I've seen, my own results from looking at the Sentinel record over the last 5+ years. I'm going to start with Pine Island Glacier, and I'm not going to talk about the importance of any of these glaciers, because I'm assuming you're all glaciologists, you're all members of the IGS, you know the implications of Pine Island Glacier and all the other places that I'm going to mention. So Pine Island Glacier is a fascinating area because it's a huge glacier that's draining a large part of Antarctica. And as you can see from this series of velocity maps, these are annually average velocity maps from Sentinel-1, you can actually see the changes that are happening in front of our eyes back from 2014 right until the present day. These are annual averages. There were 7 such coverages in 2014. By 2016, it got up to 51. Then that doubled in 2017 with Sentinel-1B being launched, and that's carried on ever since. This is an amazing record of data, and it gives you these really good quality velocity maps when you combine all those data together. But from my perspective, what's more interesting is if you look at the time series of data from points on this glacier. In this case, I'm picking this point here. It's a point on the floating tongue of Pine Island Glacier, and I'm matching up here my own Sentinel-1 results in red with those data from the measures and the ITS Live global mosaics that are freely available to anybody. So you can see business as normal down here, and only in the Sentinel record we've seen a really interesting increase in the velocity of the floating tongue of Pine Island Glacier. That's accompanied this weakening of the ice shelf and a gradual carving back of that as the whole thing has begun to weaken, as it is thinned, as it's been eaten away by the ocean. Now, interestingly, this record is really only from the floating tongue here. If I gave you a point from up here on the main trunk of the glacier, you don't see anywhere near as fast an acceleration up there. So fortunately, we're not seeing a massive change in the whole glacier, but we're definitely seeing a change in the floating ice tongue. And what I'd like to finish off with on Pine Island Glacier is show you how you can just about start to see, because you have the high temporal resolution with Sentinel-1, you have this slight slowdown in the winter months, and then a speed up in the summer, and then a slowdown. So we're actually starting to see seasonal effects for the first time in Antarctic glaciers from this absolutely superb record that Sentinel-1 has given us. So let me now move on to the next area that I show an interest in, and that's Svalbard. And I've spent a lot of time in Svalbard. I was an adjunct professor there for a while. I've done a lot of teaching there, I've done a lot of field work as well, as has Tavy. In fact, my first visit to Svalbard was with Tavy back in when, Tavy? 2000 or something? Long time ago. You don't need to answer that. And back in the day when I was working with Tavy, looking at surges in Svalbard, I had this idea that one day, wouldn't it be nice if we could show maps of Svalbard and how the surges come and go and highlight little bursts of activity? And indeed, that's what we have now. So if I just step through the years here, that's 2015, 16, 17, 18, 19, 20. And I'm just going to step backwards again here so you can see all the changes that are happening on Svalbard glaciers, and you can see how the surges are coming and going, and you can see the fast flowing features that are there all the time, and you can see the quite amazing changes that we're starting to see in Svalbard. It's basically a high coincidence, high concentration of surge type glaciers, which can really be highlighted when you can have such a concerted amount of data. Now, a couple of years ago, the Copernicus program didn't just give us this ascending data, they started getting descending acquisitions as well. So I'm just going to step between the ascending and the descending acquisitions. The descending don't have quite so much coverage, we don't get all the glaciers. And what you can see changing there is simply the illumination of the scene that shows how the mountains appear to be moving, but of course that's just the way they're illuminated. But the key thing to notice is that, of course, the glaciers themselves are not changing at all. So this shows consistency even when you've got a different look direction for the satellites. So these are glaciers that are of most interest. Some of these I'm going to talk about. Some of the ones I haven't arrowed I'm going to talk about as well. But there, if you've wanted a quick look at some of the interesting glaciers on Svalbard, that's where they are. And let's remind us that we've not just got these mosaics of velocity for the whole of the archipelago of Svalbard. We've also got these long time series of 6-day data giving us a velocity map at each time series, and of course a 10-meter backscatter image that we can also do things with. So watch how this ice front moves backwards and forwards, and watch how the seasonal changes happen on the glacier velocities throughout the year. So that may not come across from my machine up to the cloud and back down to each of you, but I hope you can see at least some of the animation of the velocities of this Kronebrain Glacier in northwest Spitsbergen, reminding us that we've got two things we can measure here. We can measure speed every 6 days, or 12 days from the early part, and ice front position as well. And now I'm going to distill out of that for a few glaciers some of the interesting behavior that we're starting to see in Svalbard from this enormous record. And just to orient you, these are quite complex graphs here. In red, we're showing the Sentinel-1 speed record here every 6 or 12 days. For some glaciers, I've also got some earlier data from TerraSAR X, which precedes that. We've also got the ice front record from Sentinel-1 and earlier from TerraSAR X. We've got the rate of change of the ice front position, the dl by dt, that other people on this seminar series have also talked about. forget who that was, but I've looked through some fantastic talks looking at exactly that dl by dt and the frontal ablation rates in the past. I think Ellen Enderling comes to mind as giving a very good talk on that. Same for Terrace RX. And just to put it in context, here's the air temperature at the nearest station and the precipitation at the nearest weather station. So what we can see here for Kronebrain Glacier is we can see this typical, reasonably fast flowing glacier with this large summer spike that happens normally when the temperature here goes above 0 and we start to get some lubrication of the glacier. And sometimes we get a second spike where we get a high rainfall event during the summer. This is typically what we'd expect of a glacier, no big surprises. But what we do have is a nice record of showing how this really does work and how the rate of change of the front here is really tracking not anything to do with the air temperature or even really influenced very much by the velocity of the glacier, but this rate of change of the ice front is tracking, of course, the ocean temperatures at depth in the fjord. As again, we've seen many talks about it in the past, not just Ellen, but Adrian, of course, talked about this a lot as well. So this is a typical glacier, and this is what we see, and we get these lovely record of ice front position. We get a movement forwards in this late winter, then a rapid retreat in the summer as the warm water comes into the fjord, and then an advance and then a retreat, and a lovely smooth record showing you how this seasonal advance and retreat is superimposed on a long-term overall retreat on these glaciers. So that may be all you think we're ever going to learn about in Svalbard glaciers from a typical non-surge glacier. But of course, we're able to look at the surge type glaciers as well. Here's a typical surge type glacier. This is a glacier I've been to many times with students. And we can see this surge happen from 2016 down to 2019. We can see we get the same sort of record of frontal position here, but just superimposed on that is this additional advance of the ice front caused by the surge. But really, otherwise, it's just affected by this gradually eating away by the melt undercut carving that's happening at the front of this glacier. Really, it's dominated by that ocean interaction. But also here, you can see another peak happening in the summer. And this, of course, is because once the glacier has started to surge, then there's crevasses all over it. And so then it is susceptible to these summer speed ups because of the meltwater and rainfall that's able to enter the glacier and get down to the bed. Now let's move on to another surge here, and this is a surge that Doug Ben talked about in his talk. He showed this animation. Again, I hope it's working for you. I know Zoom is not the best place to find animations and to look at them. So I would encourage you, if you do want to look at this again, to have a look down here in the bottom left. If you just search on Adrian Luckman WordPress, you can go and see and have a look at this animation and a few others to your heart's content. Here, hope you can see that as well, is a little model of the Eiffel Tower, because I mean, how else can you have a length scale or a scale bar in a moving 3D animation? You have to have a bit of 3D architecture there to show you how big things are. So Mawson Brain is another surge that we can track with Sentinel-1. And here, a bit messy at the beginning. I should have said these lighter traces here are where the feature tracking has worked, but I've kind of removed those automatically using the filter. So some of them are good and some of them are bad. So you can sort of filter between these two light and dark reds if you need to. But once the surge is underway, then tracking works really well. And watch how this surge has kind of exponentially reduced in the speed as we come down to the present day. And yet with these summer speed ups due to the air temperatures going above 0. So two things are happening to this glacier at once, which I find quite fascinating. The other interesting thing about Mawson Brains, it's down here on the east of Svalbard. It doesn't have so much access to hot water. So once this ice front has surged forwards, it's staying where it is because it's not eaten away anywhere near as fast as the other surges that I've shown you. Now, Monica Brain was the one Tavia and I published back in 2002, and that's undergone a second surge. Monica Brain is interesting for many, many reasons, not least because, you know, the surge is kind of half-hearted, and once it's in surge, it kind of gets kicked up here, and then it sort of slumps back again, and it thinks, ooh, have I still got some surge left in me? Yeah, I'll do it again. And it gets kicked back again. You can see it's almost in some kind of supercritical state that eventually the summer is too much for it, and probably the subglacial system gets kicked into a different state, and the whole thing grinds to a halt right after that summer speed up. So that's Monaca Brain there. But of course, as you saw from earlier on, there's a lot of surges going on in Svalbard, and there's a lot of surges we can learn from, and Doug and I are working on this. There's surges that are quite short and sweet. There's surges that we've seen before that decay very nicely. There's surges here that sort of start and then finish and then start again. There's something here going on Austfonna that may or may not be a surge, but it's definitely a speed up over a long period of time. Maybe we need to start thinking about a different classification of surges. There's a surge that happened fairly recently on Recherche Brain that looked like it was all over, but then it started speeding up again. And the reason for that is that the upper part of the glacier joined in the surge late. All sorts of interesting behavior that we wouldn't know about, because this is almost like having a GPS on every glacier in Svalbard. We all know about Basin 3 on Austfonna. That's a surge that started well before Sentinel-1 was launched, and will still be going on well after Sentinel-1 is space junk, I suspect. Another big glacier, Negribane, really big surge, and again we get these summer speed ups once the crevasses have opened. And the ones I particularly like are these two down the bottom, Sonclar Brain and Cavall Brain, that I discovered using this method. We can see these are very smooth. These seem to see and feel nothing about the atmosphere. They seem to be going all along by themselves and having their own little internal dialogue about when they want to speed up and when they don't. They don't seem to care what's happening to the atmosphere, what's happening to the ocean in front of them. Now, I've left some interesting ones till the end. We've seen the typical glaciers. We've seen the fact there's a lot of surges and a lot of variability in the surges. Well, what about these then? I'm totally puzzled by these, and I'd like to try and get to the bottom of what's happening here. There's two glaciers that are behaving like this. Hinlopenbrain up here in northwest Spitsbergen, and Stonebrain that Tatsio's published on before over here in eastern Barentsøya. And these are glaciers that seem to be kicked into action by the summer, as if they're undergoing a surge, and then they have a surge-like decay to their velocity, and then they're kicked again, and then they decay. So it's almost like it's a surge-type behavior that's being kicked off in a cyclic manner. And I'm sure we can learn a lot from this kind of behavior of glaciers. Absolutely fascinating. I hope you agree. Let's move away now. Let's move from Svalbard and let's go to somewhere else that I'm a bit obsessed with, and that's the Larsen Sea ice shelf. I'm very lucky to have been here twice with my colleagues. There's a lot of data from here. It takes about six Sentinel-1 scenes to make this mosaic of the Larsen ice shelf. And these velocity maps were very useful in tracking the departure of iceberg A68 when it left Larsen Sea ice shelf back in 2017. But we're all glaciologists. We know that that was just a bit of glaciological theatre and a bit of fun to draw people into glaciology and science and what's going on in the cryosphere. Of course, as glaciologists, we're more interested in what's happening to what's left of the ice shelf. Does the departure of this iceberg mean that the rest of the ice shelf is changed forever and will start to accelerate? Or is this all just passive ice that really makes no difference? These are the big glaciological questions that we need to answer. So of course I turn to my modelling friends like Steph Cornford. Steph, I'm sure many of you know, he uses the bicycles model, and I asked him to do this, and over an afternoon he produced this amazing model. He's very quick when he wants to be about producing models of ice shelves. And what he showed was that having tuned this glacier and then cut away part of this and checked out what the model would do to the velocities of the ice and showed the change in speed post calving, he showed that we would expect a roughly 10 centimeters per day speed up in the middle for a part of the ice that was otherwise pinned back by A68 that used to live here. and the bits either side that were otherwise holding back the iceberg or being drawn forwards by the iceberg, I should say, are able to relax a bit and slow down. So that's the modeling expectation. And so my job, I guess, is to see if Sentinel-1 is able to pick out those. So let's now have a look at the enormous amount of data that you need to process to try and look for these very small signals in an area that has very large inter-satellite imaging changes in velocity because of the tides, because of the impact of the flow of the ice on the tides, because of things like in the inverse barometric effect, where the ice shelf is going up and down just because of the air pressure above it, and all these other things. So you have to draw in all of the data here, and we can see a small number here is the number of coverages in each of these years going to make up these great smooth velocity maps. And if you then take a difference between those, so 2015 to 2016 is this one here, we can see apparently it's speeding up around here, slowing down over here. This one's got more of a slowdown over here. Really, there's a lot of noise, a lot of stuff going on here that we perhaps don't believe. And one of the reasons for not believing it is because there's been no correction here simply for the up and down motion of the ice shelf. So it's important to go through all your velocity maps that each have a different tidal change between the two images that we use to create them and correct that for the up and down motion. So a corrected detided set of change velocity maps would be these, and these I can start to believe. And we can see that I think these are believable values in the kind of range that Steph thought we ought to be seeing them. Sorry these are produced so small, but this tends to suggest to me that if anything, Larsen C has been slowing down over recent years. And what we're left with is big signals of the iceberg moving and just a big signal here of another part of the ice shelf that broke away sometime last year that some of you may have seen in my tweets and that kind of thing. So let's now drill that down to look at seeing if we can see exactly the point at which this ice shelf may or may not have responded to the loss of the iceberg A68. So this is a reminder, this is Steph's modeling result. It's almost on the same scale of colors, roughly the same as I'm presenting here. This is the raw data that hasn't been detided. If I show you the detided data, we can see a really nice pattern happening here where we do see this speed up in the center. We do see some sort of slowdown either side of that. We see some interesting changes elsewhere in the time period 14 months before the rift really advanced compared to 14 months well after the calving had gone. And a later comparable change map between the post-calving result and another 14-month velocity result shows us again this ongoing cooling of the ice shelf, slow, very modest slowdown of the ice shelf, apart from some bits that are starting to break away. So I think we have seen that signal in the Larsen C ice shelf. Okay, well, let's move on then. And let's now move to a different ice shelf, the Brunt ice shelf. And the British Antarctic Survey, who of course have their Halley research station on Brunt, excuse me, are the best to produce fantastic graphics of what's going on here. So this is the Brunt ice shelf, and this is part of the Brunt ice shelf. It's also called part of the Stancomb-Wills Glacier ice tongue. Halley 6 used to be here, but they moved Halley in the 2016-17 season over to its new site because of the growth of this rift they called it Chasm 1, that reignited and started to advance rapidly until the point at which this graphic was made in 2018. So they saw this coming. The research station was designed to be moved, and they moved it all the way over here to a safe place. But as they were doing so, lo and behold, another rift opened up. They called the Halloween crack because it appeared on 31st of October. And this really sort of sets the scene for what's been happening ever since then. And it's very interesting to go and see what Sentinel-1 shows us of the series of velocity maps for the Brunt ice shelf and the Stancomb-Wills ice tongue over this time period. So here we are, this is back in 2015, and we can see over through the years, now there wasn't a gap here, this is just data that I have yet to get around to processing. And what you can see is quite a lot of stability in the main part of the ice shelf here. But if you look at the Brunt ice shelf part of this, the part where Halley 6 ice research station sits, you can see this has gradually been speeding up and speeding up, moving away from the rest of the ice shelf. And you can see that in a difference map between 2018 and 2019. We can see this showed a massive speed up of this part of the ice. So much so that we all got very excited and lots of people started putting out press releases and excitement about saying, including me, I'm afraid I jumped on this bandwagon as well, saying it's going to calve anytime soon. But we were proved wrong. It's been hanging on ever since, even though the part of ice that still holds this greater London-sized iceberg to the remaining part of the ice shelf is only, I don't know, 2 to 5 kilometers long, depending on which data you look at it in. Even so, it hasn't broken away in that time period. And in fact, in the intervening time since then, in fact, parts of this iceberg have actually started to slow down, which I think is fascinating in itself. And part of the reason for that is that another crack has joined in. This is the unnamed rift. We can see it here by the difference in velocities. And now this part of the ice is starting to move away from the rest of the ice shelf. So there's lots of things happening here, and I'd like to indulge my passion for making time series of Sentinel-1 images, showing you how these cracks developed over time on the Brunt ice shelf. Again, I'm aware that these don't always work too well on Zoom, because my animation's got to get from me up to the cloud, and then it's got to have another pass down through the internet to each of your computers. If you can't see, if it's not working for you, then have a look on WordPress, just search my name and you can have a look at that to your heart's content. But what you can see here is the development of these rifts. And I think this is why we're really interested in looking at these ice shelves. It's not really that icebergs are about to go, because we all know that this is the normal behavior of ice shelves. They're always going to give away icebergs. It's always going to happen. This one's just particularly interesting because of the Halley research station. What we're really interested in is the rifts. We're really interested in rifts, not because of when they happen, because of where they don't happen, where we see ice shelves that seem to be held together despite the fact that rifts have started to cut through them, but they haven't really finished off the job. And that's really where the research is. So if you've got lots of examples of rifts, we can start to understand how they propagate through ice and therefore learn more about the future of all ice shelves. So now, having indulged you in that little animation over the last few years from Sentinel-1 of this area, I'm going to focus in on the McDonald ice rumples and zoom in on that to show you that we have really good quality, high resolution data showing you how these rifts are developing as this ice shelf comes across this pinning point on the seabed and is essentially torn apart by this. Why it's happening in the last few years when it was business as usual and it just really rode over this pinning point for the years before, I guess we have yet to find out. But Sentinel-1 does a wonderful job of producing these animations, and which in its own turn, I think, has a good ability for us to be able to use these to engage other people in glaciology and in cryospheric science. But let's have a look at another thing we can do with these great Sentinel-1 velocity maps, and that's look at the rate of velocity change in space, otherwise known as the strain rates. Now in 2016 we didn't have many velocity maps, so it's quite noisy, but I hope you can see, even though I've tried to show perhaps too much in this view graph, I hope you can see that you can see a bright sort of red and white stripe here as chasm 2 develops through the time series, gets longer and longer. So the rift itself is showing in the strain rate, but you can also see that there's a lot of other rifts riddling this whole ice shelf system all over the place. It's not just the rifts that our attention is being drawn to that might eventually give birth to icebergs. There are plenty of other places here where the ice is splitting apart and opening those rifts, and we can learn from those rift openings. But it wasn't until actually just after Christmas that this new rift really did begin to open up here. And zooming in, we can see that the strain rate figure here does a very good job of picking out exactly where that has got to. In fact, you can see the tip of that rift well before you can see it in any of the available optical imagery from Landsat. And we saw something from NASA come out, I think today or yesterday. They showed the latest Landsat 8 image of this rift, showed where the rift tip was. But I think even this earlier velocity map here shows it even further advanced, because the velocities are so sensitive to how this is changing. So what's going to happen to this? Well, let's have a look again back at the time series. As what Sentinel-1 is so good at giving us. It just doesn't give us these annual patterns of velocity, which themselves are very valuable, but it can show us what's happening in time. Okay, it's a noisy pattern, but let's have a look at what's happening over here, the original Halley site, where we can see this started to accelerate here, and everybody started getting very worried. But then as the Halloween crack started to open, and so it relaxed again. And so the Halloween crack started to take the strain off of this possible carving over here and open something else out instead. The new site of Halley, I think, is quite stable. Yes, it's accelerating, but it's accelerating at the rate you would expect, given that this is drifting away from the continent very gradually. But what I spotted just after Christmas was at this point here, which I've called McDonald North simply because it's north of the McDonald ice rumples. I spotted that this was behaving very much like iceberg A68 had started to behave just a few weeks before it carved away. So this was when I started to suggest that we were going to see a carving from this part of the Brunt ice shelf system. And once again, we can see how this rift has then taken the strain from the Halloween crack, because, and indeed from the Chasm 1 as well, because this is my measure of how Chasm 1, the average width over here, has been opening. It started to get wider and wider and wider and wider, but then the Halloween crack took over the strain. So it's still opening, but not as fast. And then just in the last few weeks, we can see it's completely stopped opening, and it's stopped opening, and this rift has stopped advancing simply because all of the strain from this whole ice shelf system is now taken up by this new crack on the Brunt ice shelf. So thank you for the questions that I've only just noticed are appearing in the chat. I'm going to hold those over until the end because I'm nearly finished. You'll be glad to know, a couple more minutes. This is my take about what will happen next. So Berg 1 was what we were all predicting would carve something like a year ago. We were all wrong, size of Greater London. But I think now more likely Berg 2, about the same size, is more likely to carve next, because this rift is going so fast, and because this point is clearly starting to accelerate to a point where really there's only one thing is going to happen. So watch this space, because there'll be another pair of Sentinel-1 images from this area coming along, I think on Saturday. Yeah, that's how in tune I am with the rhythms of Sentinel-1. That's what's likely to happen next. Okay, so I'm going to finish. I'm going to come right back to the beginning and talk about obsessions again. Now, once you've started doing something, it's very difficult to drop it. And with Suzanne's help, Suzanne Bevan, who I've worked with for all these years, I've kept the record of Kangerlussuaq and Helheim going. I know other people have done similar things. I don't know whether other people got such a long record. This is what we published back in the 2006 paper. And we can see how the record of satellite observation, not just from Sentinel-1, but from TerraSAR-X, Landsat, all sorts of other sources, have given us a much better view about what's happening on Kangerlussuaq and on Helheim. And although we haven't seen the really high velocities of the past. Presumably those were high because the glacier was a lot thicker then, so it had a lot more driving stress to drive it forwards when it was really first being attacked by the ocean. But we can see that both of these glaciers now are at their most ever retreated. In fact, Kangaroo's Wax 1, I think, to watch, although it's starting to eke forwards again. And again, this is where Suzanne's really watching very closely what's happening to here. Again, she's hooked on this cycle of data to find out what happens next. So we are seeing pretty much what we published back in 2006. We're seeing synchronicity between these two glaciers, which are a couple of 100 kilometers apart, just showing again, as other people have shown on this seminar series, this is all being driven by the ocean, and it's that rocking at the ice front as at the grounding line, as Eric put it. So I'm going to finish there and say thanks very much, and wake Tavi up again to say, Tavi, how would you like to deal with the questions?
Normally, we ask people to indicate on the chat that they want to ask a question, and then we call on them and get them to actually ask it verbally unless they don't want to do that. So should we start with Julian Williams?
Hi, can you hear me?
Just about.
Okay, I was just wondering if in the process you use just one of the polarizations. Is it just the HH, or do you use multiple polarizations to see where the cracks are in particular? And do you validate what areas are probably cracks as opposed to a different type of feature that looks like a crack? And also, can you estimate where the smaller cracks are and how they will meet, if they can meet, based on your strain maps to kind of tell where you'll have like a new break or predict where new break should be?
Okay, thanks, Julian. Thank you for a great set of questions. It's really nice that you've put it in the chat so I can look to my left where my chat window is there, because I couldn't quite hear everything you said, but to answer the first part of the question, the high resolution data from Sentinel-1 is not always collected in all polarizations. So I tend to use the HH when it's available, and in some cases it's not available in that as well, so I use the VV. So yes, I'm tending to use the HH where it's there. You're also asking, do I need to validate the cracks? I mean, really, I'm sharing with you today, depending on where you are, what's on my hard disk. This hasn't got close to publication yet, maybe it never will. I just thought you'd be interested in this. I do tend to look at the optical data as well, because I'm always interested in, can we see more on that? Can we see where the crack tips are? But in almost all cases, it's easier to use interferometry or the velocity maps, as long as the coherence is good, to see where those rift tips are, more than you can in the optical data, which tends to have the rift tends to be wider than a pixel, really, to be able to see that there.
Okay.
And as for predicting where these cracks are going to join and end up, I'll leave that to somebody else.
Okay.
Thanks for the question.
Thank you.
My computer helpfully reminded me that I'm muted then. Are there any other questions? If you're watching on Facebook, and there are 8 people watching on Facebook, don't forget you can ask questions by putting it in the comment there. Frank, you've got a question, so feel free to go for it.
Yeah, Adrian, great talk. I really enjoyed it.
Frank, thank you very much. From coming from you, that's high praise.
It was about this model example that you showed on the Larsen C, because the model, I assume this is an instantaneous effect on the velocity field, and you afterwards looked at the same effect to reconstruct the same effect, but I thought you used 14 months means after that. Would it be possible to look, because in 14 months the ice shelf has also relaxed and moved and deformed and whatever. So is it possible with the interferometry to look at much shorter timescales just after the calving event? Or is that too noisy?
Interferometry is very hit and miss over there, but yes, you do see some interesting patterns. As to whether the Steph's model was an instantaneous result, no, I don't think it was. I think that was a relaxed pre and post in two different configurations of the ice shelf, with and without the iceberg there, and just doing a difference on those. So that wasn't instantaneous, so I was trying to compare like with like.
Okay, it was on the same timescales.
Yes. Well, I mean, models have timescales? I don't know. It's the same geometry. So I tried to fit my observations to be a long time before the rift was even starting to change the nature of the ice shelf, compared to a while after the iceberg had gone, once it had relaxed into its new state.
Okay, good. Thank you.
Thank you.
Andre, you had a question, I think.
Oh, yes. Thank you, Adrian. Very interesting talk. Great. So I have two small questions. First is, in Svalbard, your speed fields sometimes are outside the fronts. Is it artificial because of filtering or something, or result of pushing of sea ice or something like that?
Okay.
And the second question is, you show time series for Svalbard Sea. Is it point series or some kind of averaging? I don't know, please.
Okay, both very good questions. So I think you're referring to the animation of Chronobrain that I showed, where you can see that apparently there's some velocity happening beyond the front of the ice. And yes, that is a combination of both things you said. It's partly the size of the feature tracking window, which is about 1 kilometer on the ground, and that ice front is, I don't know, about 4 kilometers wide, something like that. So it tends to smear the result across there, and you've got to be careful then about what you can extrapolate and where, and you've got to be very aware of what the true resolution of the feature tracking is. But also, you do get sea ice sometimes in front of Chronobrain, so sometimes it's also tracking that. So that was a good question. Your second question, you're testing my instantaneous recall, and I remember you were asking about are these velocities at points? And yes, as I've tried to show, I'm sharing with you a bunch of observations that I've just sort of picked off my hard disk, and I've just picked points in the center of the glacier and said, what's happening here? And it could be that on different parts of some of those glaciers, something slightly different is happening. I'm not taking, in this case, averages. They are just points, but that point, of course, represents a kilometer by kilometer patch on that ice and how that's moving. So I hope that answers your question. Is that satisfied?
Thank you.
Question from Irek. And I apologize if I mispronounced your name. Irek Sabota. And
okay, sorry. Sorry.
I probably mispronounced your name. My apologies. Please correct me so I get it right next time.
Hi, Adrian. It was nice to see you and hear you. My question is about Avansmark brain. Yesterday in Svalbard, I have seen that the Avansmark brain was marking on the map. That is the glacier with ongoing search. I'm sure it is true, because I think that the search of Avansmark was finished in 1950. It also on your picture, in what you think about it, what is your opinion about it. Is searching now or not? Because I was on September 2020, and in my opinion, it now is again recession.
Okay, I'm really sorry that my sound system here is not brilliant, and I got about half your question. I think you're asking about Avansmark brain and whether or not it's surging. We published on this one. The paper was Heidi Silvestre, Doug, Ben, and myself, we published a paper on this a couple of years back. So we definitely got a good surge on there. And more recently, it's definitely finished that surge. But this is a really interesting one that I could have shown more on, because since the surge has finished, actually the upper part of the glacier has started to activate again already, which I think is fascinating. I think that's something to do with the type of surge that's going on there, being a surge that was initiated at the front of the glacier rather than the surge that was sort of internal to the glacier and traveling downwards. So I'm sorry if I've misunderstood your question, but I hope that's satisfied you in the answer.
Thank you. All the best.
Carla has a question.
Hi, thank you so much for your talk. I was particularly interested in the beginning when you were talking about Pine Island Glacier, and that there's now, you're observing seasonal velocity variations. And I was just wondering if you'd looked at, or you'd like to hazard a guess about why you think that's happening. Do you think that is the meltwater reaching the ground?
It's always difficult sharing things that you haven't really talked about elsewhere, or even thought about writing up into a paper. I'm just putting those observations out there. Obviously, the things you mentioned are possible causes. It's either driven by the ocean or it's driven by subglacial meltwater in some way. I mean, I think it's really fascinating to find out if that signal, which you can only tentatively see in my time series, and I'm not seeing it in anybody else's, if that's truly there or if there's something else going on. I think it's fascinating. If anybody wants to talk to me about this or try and help me work this out, I'd be very pleased to hear from you. In fact, many of the observations here, some of which I'm working with other people on, but many of which I'm not. So if you're interested in having something more to do with some of these, then please do let me know.
Thank you.
Thank you for that question.
Any last questions? Could we ask you to advertise next week's talk, Adrian? Hope you got that one slide. Thank you very much. So next week we have Bea Casado talking about Greenland and capturing the evolution of the Greenland ice sheet with remote sensing, bridging past and future. Sorry. So hope to see you all next week. Any last questions for Adrian before we wrap up? I think we're all questioned out.
Thank you so much for coming. Thanks for your questions. Thanks for your kind wishes.
So thank you very much to Adrian, and thanks very much to everyone in the audience, and hope to see you all next week. Yeah, exactly. I agree. So, and best wishes to everyone in the US who is going now to have a beer or a champagne or to celebrate or whatever. So
I'll definitely applaud that one. Can I have my wine now?
You certainly can, Adrian. You definitely deserve it. Thanks very much to everyone.
Yeah, thank you.